Imagine you have a molecule, a beautiful, complex architecture of carbon and hydrogen, but there's a stubborn oxygen atom sitting right in the middle of it, double bonded to a carbon. This is a carbonyl group, the defining feature of ketones and aldehydes. Now, what if you wanted to erase that oxygen entirely? Not replace it with something else, but simply vanish it as if it were never there, leaving only two hydrogen atoms in its place. In the world of organic chemistry, this is exactly what the Clemensen reduction achieves. It's a chemical delete key for oxygen. Let's look at the basic transformation. On the left side of our screen, we have a ketone. Let's use acetone as our example. Notice that carbon-oxygen double bond. To turn this into a simple ethylbenzene, we need to strip that oxygen away. But oxygen is electronegative and tightly bound. To get rid of it, we need a specific, somewhat aggressive set of tools. Specifically, we use a reagent called zinc amalgam, which is just zinc dissolved in mercury, saturated with concentrated hydrochloric acid. Now, why this specific combination? Let's visualize what's happening at the surface of the metal. Picture the zinc atoms as a reservoir of electrons, eager to be given away. The mercury isn't just there for show. It coats the zinc, preventing it from reacting too quickly with the acid and ensuring the electrons are delivered steadily to our organic molecule. Watch what happens when our ketone nears this metallic surface. In the presence of all that strong acid, the oxygen atom gets protonated. It grabs a hydrogen ion and becomes positively charged. This makes the central carbon even more hungry for electrons. And here's the key insight. The Clemensen reduction is fundamentally a steady stream of single electron transfers. The zinc pumps electrons into the carbon, breaking those strong carbon-oxygen bonds piece by piece. As the bonds break, the oxygen leaves as a water molecule, and the carbon, now sitting with a negative charge, quickly snaps up protons from the surrounding acid. Notice how the carbon never becomes a standalone radical for long. It's a controlled, stepwise transition from a carbonyl to a methylene group. But there's a catch. Because this reaction requires concentrated hydrochloric acid, it's a bit like performing surgery with a sledgehammer. If your molecule has other parts that are sensitive to acid, like an ester or an alcohol, the Clemensen reduction will tear those apart too. This is why chemists always look at their entire molecular neighborhood before deciding to use this tool. If the molecule is acid-sensitive, they might choose the Wolff-Kishner reduction instead, which does the same job but in a basic environment. So the next time you see a hydrocarbon chain that used to be a ketone, think of the Clemensen reduction. It's a reminder that in chemistry, even the strongest bonds can be dismantled if you provide the right surface and a steady enough flow of electrons. It's not just about changing a molecule. It's about the precise, calculated removal of the old to make room for the new.